It looks like everyone is here, so let's get started. It's my pleasure to introduce Walter Dempsey from University of Michigan for the next talk. Walter is the assistant professor in biostatistics at Michigan, but has deep experience with mobile health data and statistical analysis for mobile health, including missing data, which is what he's going to be talking about today. In part, at least, due to the many bugs in my software that he has had the pleasure of dealing with. But I'm hoping I'm not the only one responsible for his understanding of missing data. But we're looking forward to hearing what he has to say about how to handle missing data in a mobile health. And yeah, Walter, take it away.
Thanks, Peja. And no, you are not the only one that that has led me into the world of missing data in mobile health. It's much more pervasive and ubiquitous than I had originally thought before sort of entering the area. But yes, as Peja said, I'm Walter Dempsey. Mostly I work in the area of mobile health and specifically in statistical methods related to mobile health. And so today I'm going to focus mostly on missing data and approaches to handling missing data. I know the background is quite diverse as part of the program. So what I thought I'd do today is sort of a mix of overview. So what kinds of missing data could you expect to see in a mobile health setting? Some basic missing data methods. So things like multiple imputation using change equations. So this program called MICE. And then just end with kind of an overview of specifically, I know a lot of you are interested in mobile health intervention work. And so I wanted to sort of ring some alarm bells around time-varying treatments with missing data and imputation models. So that's sort of my high-level overview of what I want to do today. So let's just start with some intensive longitudinal data. I just want to focus on a definition and then talk about the prevalence and then jump into complete case, some missing data assumptions, imputation, and other topics. All right. So what is intensive longitudinal data? I assume most of you have seen a definition. You know, it's longitudinal data collected intensively over time. So what I'll focus on at the beginning of this talk is just a very simple example of intensive longitudinal data coming from a study called Break Free. It's a smoking cessation study. It's a mobile health smoking cessation study in which we're following individuals 4 days before their quit date and then 10 days after, using wearable devices as well as self-report. And in this picture right here, I'm just focusing on the self-report side of things. What we're doing is 4 times a day, we're asking individuals to report a bunch of different items. We're asking them to report whether or not they've smoked in the recent past. So that's where you'll see these green, these circles are 0 cigarettes reported. The triangles are 1 cigarette or more reported. And then they're also filling out a bunch of items related to positive and negative affect, urge, and things of that nature. So roughly speaking, you should think of the intensive longitudinal data. The typical mobile health intensive longitudinal data is you pick blocks of time throughout the day, and then you're going to ping someone on their phone. And naturally, you're going to ask them a bunch of questions, or at least a few questions. Here, I think we asked roughly 24 to 30, somewhere in that range, number of questions. So you're getting a lot of questions each time you answer one of these surveys. And this is just one individual's data. So I just wanted to show you what the data looks like before we talk about missingness. So this is for a given individual in the study. I've taken all the items, so positive emotion and negative emotion items I'm showing here. There's also questions about urge and a few others, but I'm taking positive and negative emotion items. And what I'm showing you is the trajectory of those items standardized. So meaning I take the average of each of those items and I delete those so that they're sort of all on the same scale, roughly speaking. And then in the bottom one down below, you'll see the number of cigarettes reported at each of these item times. So you'll see at the first 2 times, the person reported a couple cigarettes being smoked, but then at the time around 2.5, they smoke a little bit more. And there's a few times in here when they actually report not smoking at all. But you can see sort of the first point I want to make is the complexity of the data. So there's over 20 items as well as smoking data coming in. And so we want to model potentially the relationship between these different variables. So let's just say that was our goal. Now, where does missingness come in? Well, I just want to remind you, in this study, I was supposed to get 4 EMAs a day. If you look at the plot above, you'll see the pattern of EMAs is not 4 a day, but people are responding, this person's responding twice on the first day, then they disappear for a while, then they reappear and they answer 1 question. Then we get 3 responses in a row on one day, 3 on the next. And so you're actually having a lot of missing data, and it's just not present in this picture. So the first point I just want to make is often what you'll see in EMA data is that if you ask an individual, well, how many times did you ask the questions of how many times did you ask for self-report? They'll say, we asked for self-report 4 times a day. But if you then go and ask them for the data, they'll give you the complete data, not the times that they asked for the information and they didn't get any recorded EMA items. So my first little bit of advice, just in terms of designing data collection, is in this particular study, we were able to actually know when did the system prompt an individual to fill out a self-report, and why was, excuse me, why was the individual not filling out the self-report, at least up to some items. So we know, was it a bug in our software? So did we just not send an EMA? Or was it because the individual received the EMA, but then just decided not to fill it out? So in each of these cases, you should think that there's actually multiple EMA times throughout this study at which we didn't receive an item or a set of items. The second thing I just want to point out is this study was supposed to last 10 days. But you can see that for this individual, around day 8, they just stopped responding. And so some people in the study will respond for a few days and then just stop responding to EMAs completely. So we do have a dropout kind of missingness as well. And so we also want to be considering not only individuals' missingness with respect to they just didn't fill out a survey at a given time, but also they might have dropped out of your study early. The last piece I want to mention in this example here is that we have the number of cigarettes smoked. And what we asked them is the number of cigarettes smoked since the last EMA time. And I just want to point you to one example, which is on day, I believe it's day 4, the individual reports not smoking or smoking 3 cigarettes in this first EMA, then 0, and then 12. Now, the question we'd ask ourselves is, this is less of a missing data problem and more of a question of, is it reasonable to when you collect this data to say, okay, 12 is correctly measured from this individual, because they're saying they smoked 12 cigarettes in about a 2-3 hour window. And so we just want to be careful when we think about missingness to also think about measurement error as well. And I'm not going to talk about it today, but I just wanted to point that out, that that's something else that comes out of a lot of these types of studies, is measurement error problems. So you might ask me, well, Walter, is this just a problem with this particular study? What we're seeing missingness across the board. You know, we're seeing missingness in that they're not responding to all the EMA times. We're seeing dropout. Maybe it's a poor study design. Maybe that's what's going on. I'm just going to show you 2 more examples of why this is sort of prevalent across mobile health. So the second example I'd like to show you is an example coming out of a study called the Intern Health Study. This is following over 1,000 medical interns for about 6 months, trying to provide interventions to improve mood, increase physical activity, as well as improve sleep or increase the amount of sleep on medical interns who are sort of in a high stress environment. And what I'm showing you here is a map of, or a figure representing the percentage of users with at least 1 non-missing observation per week. And when I say non-missing observation per week, I just want to tell you that the study design asked a mood question on a daily scale. So daily you would get a mood survey. Every day you were asked to wear a Fitbit or a wearable device to measure step count. And every night you were asked to wear that wearable device to measure your sleep. So in this particular study, we have multiple types of missingness. We have missingness because you didn't fill out the self-report, but we also have missingness because if you decided just to not wear the wearable device, we just can't measure your step count. Also, if you decide not to wear the wearable device at night, you just can't measure sleep. And so what we see, and this is very typical of these types of studies, is we see very low missingness, at least early on. And by very low, I mean it's roughly 90% of the time they're responding on week 1 to these mood surveys. And most people are wearing the device at least 70 to 60% of the time. And then over time, you see this dropping down in terms of the percentage of times with at least one non-missing observation. So we also have a pattern of missingness that evolves over time, which makes sense, right? If I think about asking mood questions, after about 3 months of being asked the same mood survey every single day, I might habituate to receiving it, I might become busy, I might just not want to respond, and so I just might ignore the mood surveys. With wearable devices, it's a little different, which is the wearable device, some people just don't like wearing them, so there's that issue. But the other problem, and I just want to point this out, is that if you want to measure step count and sleep on the same wearable device, you need to charge wearable devices at least at some point during the day. And so what ends up happening in these types of studies is often individuals will wear the device during the day in order to then, and then they have to charge it overnight, so you won't have sleep data. Or they'll forget to charge it overnight, so they'll charge it during the day, so you miss their step count, and then you might get sleep data because then they'll put it on for the sleep portion. So you'll have this sort of pattern of missingness, and actually the missingness in step count and sleep are related because of this battery life issue that I just mentioned. So this is another example of the prevalence of missing data in mobile health. Okay, I'll show you one more example. So let me just pause for a second. So this study here, I just want to say that the wearable data is coming in at the level of the daily step count and daily sleep data. But we're also maybe interested in more proximal or short-term outcomes. And so in this case, I'm looking at a digital monitoring of individuals who have been hospitalized for elevated risk of suicide. And in that population, you might be interested in, say, missingness of electrodermal activity or physical activity, because you're trying to understand the relationship between suicidal distress and maybe how active is the individual, thinking that what you might see is like an increase in EDA right before a high level of suicidal distress, and so you'll see signals of that type. And in this case, if you're thinking about measuring at that finer time scale, you're more worried about missingness of the sensor data on that shorter time scale. And so what this is showing you is missingness of the patient average fraction of missingness in 30-minute EDA and activity data respectively. This should say activity data on the right. And what we see is that it's a little bit less frequent, so it might be ignorable in some cases, but we do have some missingness at all times and a lot of missingness in the physical activity, more missingness in the physical activity measures. So here we're measuring a thing called activity index that's measuring your level of activity in the recent past. And so we can already see that we're getting a 10 to 15% missingness going on here. And the question is, why do we see that missingness? Is it because of battery life issues? Is it because the person's not wearing the device? Is it because the sensor is breaking? Is it because they're not wearing it correctly? There's many reasons for missingness, and we want to understand why is it missing. In this particular study, I just want to point out that it was wearing a device where they were also measuring suicidal distress through a button press. That same button was used to turn on and off the device. And so sometimes when you press the button to identify a moment of distress, you also would turn off the device. And so a lot of this missingness ended up being because of this relationship between the buttons for suicidal distress and the button to power on and off the device. So in this case, we actually learned something about how to measure things more appropriately, and the missingness came more from how we were measuring a different variable of interest. So I like memes, and so I thought I would I have this one in a couple of my talks now about mobile health and missing data and messiness. And that's just that you do not simply analyze mobile health data. And so when I think about missing data problems in context of mobile health, I think roughly speaking of 3 different buckets, and they can all have their own challenges. So when I think of missing data, I can think of EMA. So my first example was ecological momentary assessments and missingness that is due to not responding to EMAs sent at given times. And what we want to understand in that context is, why did they not respond to that EMA? Was it a technical glitch in the system, which can often happen? So for example, was it I wanted to send them an EMA and it just never got to them because of Wi-Fi issues? Did my system that I had pinging them just not work for some reason? Or if I know for a fact that the message was sent, did the person swipe it away? So maybe potentially they're not responding for more important reasons like habituation or burden. In the second case, we have wearable sensor data, and there we also have missing data problems, and we have them on two scales. So my two examples I was showing you are two different scales of missingness. On the first scale, I have daily level summaries that might have missingness. Those are often due to not wearing the device, for example, but not wearing the device might also be correlated with whether your sort of health outcomes, generally speaking. So in a sort of simple example, if I'm not being physically active and I'm being sort of sedentary, maybe I'm less likely to wear the device. And so missingness might be related to my level of sedentary behavior, and that would be a problem. In the third example, we also have wearable sensor data, but in that context, what I'm worried more about is more minute-to-minute or frequent issues. What really has changed? Okay, my headphones just went off. Let me plug in my other headphones. Okay, that should work. Okay, hopefully you can hear me, and if you can't, just let me know in chat. I'll continue until you tell me otherwise. So with the wearable data, we're worried about the daily level summaries, which can be due to missingness, but we also might be worried about proximal outcome definitions or more short-term measurements. So minute-to-minute step count. In this case, I was interested in EDA on a 30-minute or a 15-minute scale, activity index on a 30-minute or 15-minute scale. And in that case, what I'm more worried about is missingness in the local scale. And so I might worry about things like packet delivery issues. I might worry about battery life. Am I sure that the person was actually wearing the device at this time or not? A lot of wearable devices, if you're not currently physically active, you just might not get data at that time. So you might have to distinguish between missingness, meaning data that's actually missing because the person wasn't wearing the device, and true zeros that just weren't recorded. So step count that is truly zero, but you just didn't see it because the device didn't record it. And then the last sort of case is more of a traditional study design issue around censoring, which is a lot of people, you ask them to be involved in a mobile health study, they say yes, and then they don't realize how much that entails in terms of the wearable devices they might have to wear, the number of EMA responses that you're asking for. And so they just might quit the study after a shorter amount of time. And so in that case, you might have censoring and therefore missing data due to sort of censoring over time or early exit from the study. And in that case, you might also be worried about the fact that people you're seeing later in the study are conditional on the fact that they haven't left your study so far. And so you might be worried about that. So my advice for all of these is, and this is something that I try and live up to, but I think it's sort of an ongoing thing that as you learn about your devices and systems that you're using in mobile health, you become better and better at it, but never perfect, is record everything, not just what you observe. And what I mean by that is a lot of the times we have recordings of the EMAs they filled out, but we often forget to care about what we didn't observe and why. So if we really want to understand EMAs, we need to know when did you send them and why didn't they actually respond to them as best as possible? Was it because it actually never was sent, or do we know when it was sent and it was just not filled out? Things of that nature will be very important for filling out missing data and feeling comfortable with sort of missing data assumptions. With sensor data, I'm more concerned with knowing things like, did the person actually have the wearable on or were they not wearing it? How can I distinguish between true zeros in step count and zeros that are coming from the person not wearing the device? These are kind of questions that I might have to deal with. And in that case, ahead of the study actually being run, we want to make sure we have all of those measurement specifications in place in order to actually disentangle all of these issues after the study's been run. And so I think this is really, honestly, the most important aspect of missing data for mobile health is sort of pre-study understanding and figuring out why we might have missingness and making sure we have all systems in place to record the reasons why. Because if we run a study and we don't know, so in studies I've been involved with, I'll find out after the study's been run, we were supposed to send them 4 messages a day. But if they didn't respond, we just never recorded it. So we actually don't know when was it sent, why was it delivered or not? Did they not respond? Did they swipe it away? And in those contexts, you're sort of you just have to make stronger assumptions about the missingness in order to proceed. And so this is why I sort of think of us as like a priori one of the most important things to think about. Okay, so this is the main slide, I think, in terms of my advice to you, and where I put most of my effort is sort of doing it good on the front end. But I wanted to make sure I spent some time talking about missing data and how to handle it in the context of analysis and more traditional statistical methods, as well as methods for mobile health data. So I know that you have sort of a wide variety of backgrounds. And so I wanted to focus on the basics for the next about 15 minutes, and then talk a little bit about when you run an intervention study in mobile health, what are the other sort of problems that might come up. So what might you do? So let's just think of a study in which I might be wearing a device, but I want to look at daily step count. And in that case, maybe I wear the device some days and I don't wear the device others. So I have daily step count, but I have missingness. This example I have here is a much more traditional longitudinal study in which I have maybe air quality, and I'm looking at ozone levels and wind rates and temperature, and I might have missingness in that data set. And I just wanted to show it because it's a very traditional example, and I have all the code here that you can run. And so I wanted, for those of you who are less familiar with missing data mechanisms, for you to just have this code. It's, it's printed on the slide, but you can copy it, and the air quality data is available in R. So if you want to practice and just try this out, it's one way to sort of get started. And one of the issues you'll already see is that you have missingness at the daily level of ozone and solar. And so that missingness pattern is different for ozone than it is for solar. And if we're thinking of a mobile health study, we might have daily level data on different things. So we might have physical activity, we might have heart rate variability, we might have just the overall temperature, the average temperature in the location that the person was in. And so we have all these daily summaries, and you might want to do something with it, like fit a regression model of physical activity on heart rate variability, just as an example. And if there's missingness, we can't do it directly. So what ends up happening when you run regression models in R? So this is an example where I'm running a regression model in R of ozone against solar, wind, and temperature, is it doesn't actually tell you anything is wrong. So it can take in data like this, and it'll run the regression for you. And under the hood, what it's doing is it's just ignoring any row that has NAs. So if you have no ozone, or if you don't have solar, you can't be involved in the model. And so it's only going to look at those rows that have complete data. And so this is what we call a complete case analysis. If we're thinking of a mobile health project, what it would be saying is, okay, I'm only going to look at those days where I have complete heart rate variability and complete step count data, and fit the model only on that components. So this is what I'm saying here. The problem with this, from a perspective of analysis, is that you might be making pretty strong assumptions about why the data is missing. So what assumption you're making is that the data is missing completely at random. So what is that assumption? Roughly speaking, I just wanted to give intuitive level definition. It's the probability of having a missing value is unrelated to missingness or observed values of the data. So what I mean by that is that if I'm thinking about missingness in mobile health, I might have an individual who, let's just say, randomly, by every morning, personally, I'm a forgetful person. I own an Apple Watch. Today, I just forgot to wear it. It had nothing to do with anything else. I just, life and stuff. And so in that case, the missingness has nothing to do with my level of physical activity that day. It has nothing to do with my mood or anything that I might care about. And so in this case, it's just a coin flip. Every day, there's a 50-50 chance that Walter wears his wearable device. In that case, it would be missing completely at random. And so the complete case analysis would be okay. You'd have a loss of efficiency because you're throwing away data, meaning you have larger standard errors potentially, but you won't have any bias. So examples in mobile health that would have missing completely at random would be the example I just gave. Another example where you'd have potentially missing completely at random is when your sensors just die and it has nothing to do with the individual, unless you think that them remembering to charge their device has something to do with the outcomes that you care about. Another example would be just system bugs. So the person's wearing the devices, they're wearing their Fitbit, but Fitbit, just the system, the server went down for the day. So in that case, I'm wearing my wearable device. I have my data being collected, but Fitbit or Apple Watch just messed up and threw it away because their servers went down. So in that case, I could also potentially assume missing completely at random. But in many contexts, we don't feel comfortable with the missing completely at random assumption. So examples where that would be true are if I'm asking about positive and negative affect, maybe I'm concerned that if my urge is high and my negative affect is high, I'm less likely to fill out the survey. So in that case, I wouldn't have missing completely at random. And so if I just did a complete case analysis, I would have potential bias. So formally speaking, I just wanted to have, I'm a statistician. I have to have at least 1 to 2 slides with math on it, or else it's not a talk by a statistician. So I just wanted to formally define these things for you. So if I'm thinking about data on a participant, so my Z is observed data, and I also have missing data. So I have these 2 pieces. Missing completely at random is the probability of it being missing given Z doesn't depend on anything related to Z. So it's the coin flip example I just gave you of just, it has nothing to do with my physical activity, what data you missed. It's just the fact that sometimes I forget to wear my device. A weaker assumption, and the assumption that you can make that you can then start talking about imputation methods, etc., is the missing at random assumption. So missing at random is an assumption that you probably have heard of before. And that assumption is that conditional on both the observed and the unobserved variables, the probability of it being missing is conditionally independent of the missing data given the observed data. So in this world, what you would think of is, well, yes, maybe it is that me wearing the device has something to do with my level of physical activity, but conditional on the observed physical activity. So on the other days I observe Walter's physical activity, I have conditional independence. So it's not like today I've decided to be inactive and therefore I've taken off the device. Instead, maybe what I've done is just I have an overall level of physical activity, and so my probability will depend on that, but it's conditionally independent of the missing data given the observed data. And so what I'm going to show you in terms of multiple imputation approaches, the missing at random and missing completely at random assumptions make the multiple imputation that I will talk about valid. And so we often don't feel comfortable with MCAR or missing completely at random, but we might feel more comfortable making a missing at random assumption. And often what we might do is we might design the study so we collect data to feel comfortable with the missing at random assumption. So we might inform the design, the desire to deal with missing data might inform the design of what kind of data we collect. The one that's the hardest to deal with is missing not at random, or MNAR, MNAR, whatever you want to say. And this is a setting in which the missingness depends both on the observed and the unobserved data. So a setting in which that would be true is, again, the example I'm giving of if I every single morning decide what kind of day I will have. So I'm going to be physically inactive today, and therefore I'm not going to wear my wearable device. In that case, the probability of missingness will depend directly on the missing data, and therefore the multiple imputation can't handle that. And so I'll just mention at the very end, because I'm already at 3:30, a discussion around sensitivity analysis you'll do to your conclusions to deal with this MNAR potential assumptions that you would have. Okay, so if we're feeling comfortable making the missing at random assumption, or MCAR, how can we move forward? So let's just go back. I want to show you one more time this data set. So if I'm looking at positive and negative emotion, maybe I'm interested in modeling their joint dynamics. If I feel comfortable with missing at random assumption, what it's saying is I can, again, if missing at random is the probability that you missed the EMA at this time is conditionally independent of the missing data given the observed data. So if I feel comfortable with the missing at random assumption, there's 2 different ways I can go, and I'm going to show you one way to go first. One way to go is to just do maximum likelihood estimation, which is I specify a joint, in this example here, I'm specifying a complete joint dynamics for the system. So meaning I have a model both for positive and negative affect over time, and I have measurement models for the different items. So in this case, what I'm doing is I'm building a factor model, a latent factor model, and I'm modeling both positive and negative affect as something evolving over time, and the measurements are conditional on your current level of positive affect. What will be your response to happy, joyful, and enthusiastic? And under the missing at random assumption, I can feel comfortable just modeling the observed EMA items. I don't have to worry about the missingness because the missingness will factor out in the likelihood. So just to talk about what the results are in this simple example is if we feel comfortable missing at random and I use a full likelihood method, I can then say, okay, under that, joy is positively correlated with positive affect, which makes sense, and that positive and negative affect are actually negatively correlated. So over time, as positive affect goes up, negative affect will go down. And so this is a conclusion you might come to. But again, that's conditional on the missing at random assumption that we're making. And so whenever we state conclusions in this fashion, we need to make sure we also state what the missing data assumptions are. But the method that I want to talk mostly about today is multiple imputation. So in this case, what you're doing in this full information maximum likelihood is you're actually writing down a full likelihood for the data generating process. You're saying, okay, what is the actual underlying stochastics and the joint model for all these different pieces? But what if you want to do something more like my air quality example, which is I just want to fit a regression of one variable on another. I don't want to specify a joint likelihood and do all this extra work. So if I don't want to do that, if I don't want to go full maximum likelihood, I can actually do what's called multiple imputation by chained equations. I'm assuming most of you have at least heard of this. If not, I'm going to give a very simple example and give some very simple code. Again, my goal is for those of you who haven't seen it before to have some basic code and a really small data set to play around with. But for those of you who are more familiar, kind of at the end of, for the last about 10 minutes or so, I'll talk about how to sort of change mice a little bit, both to deal with longitudinal data, but also to deal with longitudinal data with time-varying treatments. So the short overview of multiple imputation, what are you going to do? Well, what you're going to do is you're going to create K, usually 5, maybe 10 complete data sets where each data set contains no missing data. So you're going to create 5 examples of that data set I showed you before of air quality, where the missing data is filled in with different values. After doing that, you're going to then take each of those and analyze them separately with your method. So in this case, it was linear regression of ozone on those other variables. And from those, you'll get both point estimates, so you'll get your beta hats, and you'll get your standard errors. So now I'll have 5 point estimates and standard errors from each of my 5 complete data sets. And what multiple imputation does is it just gives you a method for pooling those back together to get one overall estimate and a standard error on that estimate. So in short, what multiple imputation is doing is it creates multiple imputed complete data sets, and then it's a technique for combining those imputed data sets to estimate, give one overall estimate of, say, a regression parameter of interest. So the huge positive of multiple imputation is that it always can use your original analysis approach. So in the case of my linear regression, I get to keep using my linear regression. I have my complete case approach using linear regression. I get to use it on all of my complete data sets. The negative is it's a little hard to figure out how to do multiple imputation to create these in a valid or statistically principled way. But the nice thing is, for those of you who don't want to who don't want to delve into the details around these multiple imputation algorithms, there is packages called, one is called mice, is the one I'll focus on today, for actually implementing these. So this is just, for those of you who are more visual learners, I just wanted to visualize what multiple imputation is doing. So just to remind you of my simple example, I have missing data here, here, and here. So in my case, this is ozone, but let's just think in wearable land, this would be daily step count and daily heart rate variability and a bunch of other variables, month and day, and maybe temperature. And so in this case, what I might have missing step count data on a given day. And so multiple imputation would build 5 versions of this data set with different imputed values for the missing variables. And then after that, it's going to take all 5, and I'm going to just pretend that these other 4 don't exist and just run my linear regression directly on that. So I'm just going to take this complete case data set with its imputed values and fit my regression. And so I'm going to get 5 different models that I fit with 5 different regression parameters. And then there's just a method for combining them. And again, I said I'm a statistician. I have to have at least 2 statistics slides, and here's my second one. So these are the beta hats that you'll get out from this method. So you'll have beta hats for model 1, model 2, model 3, model 4, and model 5. And that's going to be my beta hat J, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And so the question is, how do I combine them back together? And the basic idea of multiple imputation is just, I have beta hat J1 through JK. What I'll just do is I'll take the average of them. So if I'm looking, for example, at the intercept, I have 5 different intercept values. What the best thing to do would be just take the average of those 5 different intercepts. For these standard errors, you have to be a little bit more careful. You have to account for both the within variation, meaning within a particular complete data set, what is the standard error on the intercept, as well as the variation in the beta hat, so the between imputed version, the between imputation variation. And so you can think of this as a within and a between, and you're just combining them together. And so this is called Rubin's rule, and it's existed for at least 30 to 40 years. So it's a very simple technique to do, and it gives you a way for, again, doing simple analyses with when you have missingness and combining them back together. To do this, it's pretty simple in R, and I just wanted to give you some basic code to do it. So in this case, I'm using the library called mice. What you can just run is just run mice on the air quality data set. And what it will do is it'll just impute all those missing values. So just to remind you, I had missingness in row 5 of ozone and solar. And so what I'm showing you here is that row 5, it's going to impute 5 different values of ozone. And so I'm just showing you for 5 those different values. If you did this with the air quality, which is my other, or sorry, not air quality, solar. So instead of ozone, I wrote solar, you'd have different missing values, but you'd have the same overall thing. And it's just going to tell you what those missing values are. Once I do this, I now have my complete data sets, and I can just run with imputed errors, run my regression model, and it'll actually spit out all my 5 different models. And then I can just summary pool them together. So just to walk you, those who have not seen the R code before, through this, it's really simple. All you have to do is run mice on air quality to create those data sets that you want, the imputed data sets you want. Then I'm just going to run my regression model on each of them separately with this command here. So I'm just taking each of those 5 and running those regression models. And then I'm pooling them back together to get my final estimates. So if I'm looking at this, the intercept value will go down a little bit. If I look at, I think the one I want to show you most is solar. So solar here with the multiple imputation has a estimate of 0.059 and a standard error of 0.024. If I look at the complete case analysis, let's make it the big one that you could actually, oh, I don't think I have a big version close by. It was 0.05, 0.06 and 0.023. So in this example here, it's not making a huge difference on the estimates and standard errors, but it's also because there's not a ton of missingness in this data set to begin with. But if you have a lot of missingness, there's a potential for improvements and changes to these estimates that you might see. And now we're getting to incorporate all the data, not just the complete cases, which means I'm actually making that missing at random assumption, not the missing completely at random assumption. Okay.
I have a quick question.
Yes.
Is there a way to constrain so that it only gives realistic variables? So for example, when I, from one of my things is like binge eating, and binge eating by definition over a 2-hour period. So it can't be 4, and it can't be, you know, it can only be a certain number, a set of numbers. Is there a way to set it in there that like, here's the range of values that can be imputed?
You can specify like the type of variable it is, so like a count or a binary, things like that. So there is ways to specify the variable type. I have not dealt with one. So for binge eating, would it be like there's a range that you're focused on, or is it like?
Yeah, if I wanted to impute like the number of times that they say it happened in a day, well, it can't be like 30. That
So what the model will do is it will, so that this is one of these this part, right? So you can tell it that it's a count variable, for example, right? So the first thing will be it's a count variable, so it has to be it can't be like 5.2 binge eating episodes. But what you can then do is so the mice will automatically try and fit a fully conditional model. Roughly speaking, what that is it's trying to say, okay, I want to impute binge eating given all my other variables. And so it'll fit kind of like a Poisson. If it's count, it'll be like a Poisson regression kind of model. And in that case, what it'll try and do is estimate that. Now you might say, I want to make sure it's estimating things that look right. So in that example here, you might then plot out, so you'd run like head of your binge eating, and you'd look and see, is it imputing values that make sense or not? So that'd be the easiest way to do it, is just see if mice is imputing values that are reasonable. I would suspect it would probably impute values that are reasonable. I have not tried to constrain it directly to say like you can never go above some number. But I think you would likely end up with reasonable predictions, as long as, if most binge eating values are between, say, 0 and 10, mice will probably not, will likely not impute values that are way outside that range.
Okay, great. And if there's like no negative values in a data set, it probably won't go negative.
Yeah, and I don't want to speak for, I don't want to say always, so that's why I'm saying probably. There are ways to constrain what mice is actually doing under the hood in terms of the imputation models you're using, so you can kind of hand it models to use. But out of the box, it's going to just try and guess a good model for each of these different different missing variables. Does that answer your question?
Yes, thank you.
No problem. Yes, it's 3:42. So I want to make sure I leave. My goal is to leave 10 minutes for questions, but please ask me as many questions as you like. I'm happy to stop talking and answer them as we go through. I only have a few more things I wanted to say anyway, so this is great. So the nice thing with mice is it's out of the box. You can often just use it directly out of the box on your data set. You don't have to think. I mean, you should always put thought into running mice, and as the question sort of alludes to, you don't want to fit models using mice that don't make sense. But often the imputed values using mice out of the box are pretty good, and so you don't really have to. I like to say probably, or most are often, it'll work well in practice. It might be slow if your data set's quite large. So for example, if my data set is large because I'm using sensor data and I have millions and millions of records, mice can be sort of prohibitively slow. So there is some issues with data set size that I've run into using mice. But if you're looking at, say, intensive longitudinal data on like a couple hundred participants, it'll be slow, but it'll still run and it'll still work. The other thing I wanted to say, okay, so what I wanted to end with, before I have two more points and then I'll stop. So my 2 points are, so what I just showed you is multiple imputation of a data set, which is actually technically a time series. So it's all these variables collected at one location, I believe New York, air quality over time in the 1970s. But of course, in mobile health, we have longitudinal data. And so one of the concerns would be, how do I account for correlation of these measurements across time? So if you had data in a long format, meaning every row was a given time point for a person, the mice will just use that current time point to impute values of those items within that time. So for example, if I have just my happy item is missing at a given time, mice will use the other values at that time to impute my happiness score. But of course, you might say, well, actually what I want to do is I want to use my happiness scores at the previous and the previous EMA time and the next EMA time to do a better job. And so in that case, you can still use mice, but the nice thing about it is you can just create a data set in wide format, where your rows are the individual. So in this simple example I'm showing here, I have data on an individual, so 4 measurements at 4 different time points, but I can just create a sort of long format to do the imputation of the missing values. And so in this case, by putting it in this wide format, I can account for the correlation within the individual. I see another question in the chat. Let me see. Okay, what is the pragmatic level of missingness beyond which imputation is not advised? It's a good question. So there's a level at which it doesn't, I would say it's usually like, you can handle it is like 10 to 30%. I've seen being able to, 10 to 30% you can usually handle. I've never tried up to 50% missingness before, but I mean, it can handle it. The question is, you'll start having to make strong modeling assumptions to like for example, if you have a lot of missingness because of dropout, and you're trying to impute just a huge window of dropout, that's probably going to be hard to do. But if you have sort of sporadic missingness, so they have 5 items a day and they just always miss one of them, then I think you won't have as much of a problem. So I think that's sort of why I'm struggling to give a general answer to your question, Arjun. But it is what I've seen is usually under 10% is easy. 10 to 30 is roughly you can handle with mice. Above 30, you're starting to just basically rely on the modeling assumptions that you're using for the imputation as much as anything else. And actually, the example I'll show you at the end is an example where by the end of the study, we have roughly 60% missingness, 50% missingness. And so we're really concerned with using imputation. And so we do a bunch of sensitivity analyses to potential dropout, and so model misspecification and things like that.
So Walter, just to sort of like piggyback on that, and this is a great exposition of a hands-on experience. So would you imagine that like maybe for EMAs and surveys, right, 10-20% of a missingness is just about okay to impute, but when we look at variables like heart rate, sleep, and things, it's possible that sometimes people don't wear the watch for half the time. So in that case, do we go with complete cases for those 50%, or what's the wisdom here on this? I know it's a
I'll give you my
but...
attempted wisdom, and then we can go from there. So I think so I have 2 different pieces of advice that I've given people in the past with missing sensor data. So if it's because okay, let me start with one thing. It depends on the level of aggregation we're talking about again, right? So if we're talking about aggregated daily step count, then it's often what you're concerned with is like, if the person didn't wear it for half the day, how do I talk about a daily step count? That's often a concern. And sometimes what I've seen people do is just scale up that value to sort of deal with that. And that's a haphazard, but often can be okay way of doing things. If you're really focused on understanding like minute-to-minute level data, and you really want to understand, but you're dealing with missingness and say heart rate variability. So in my example I gave you, what I was interested in is the relationship between suicidal distress and activity, and electrodermal activity and physical activity. So I wanted to understand, did physical activity prior to a moment of distress, was it sort of predictive of a moment of distress? In that case, as long as you, if the missingness isn't too bad, what I was doing is I ended up sampling the non-event times. So I take at times when I don't have suicidal distress, and if I have missingness, it's usually in around 10 to 20%, and I can actually impute. Usually it's not consistent, so usually it's like a person will have a little gap in their activity index because the sensor broke. So those ones I can impute using different types of methods, which they're basically extensions of mice to sensor data and other types of multiple imputation methods. But if it's completely missing, meaning like there's just no data there, I had to throw it away, and I had to make an assumption that those windows of time are basically due to they're just not wearing the sensor correctly, or something's going on, or you not wearing the sensor is sort of independent of the rest of the processes. The reason it was okay for me is because they were all hospitalized inpatient units, and so they had to wear the device unless they were dealing with some other issues. And so I felt pretty comfortable with the complete case being close to okay. But in the wild, if you had, say, post-hospitalization, you'd have to be more careful, and maybe you'd include more variables to get, that you collect to feel comfortable with like a missing at random assumption.
Awesome, thank you.
Of course.
That's really good wisdom, thanks.
Of course. So I'd like to, oh, I see another question, someone, Jesse?
I have a question. Yeah,
yeah, go ahead, hi.
Hi, good to see you. I am curious whether you really think that sensor data is like ever missing at random. So your hospital example actually seemed like a good example of like maybe it was, but when we've done like preliminary analyses on our sensor data studies that are looking at things like the relationship between baseline perceived stress on the perceived stress scale and amount of missing data, or baseline symptoms of mania and amount of missing data, which is obviously a kind of crude analysis, but they're related. I mean, I don't know. It seems like in not very big sample sizes. So that kind of, I don't know. It always concerns me. Every time I'm working with this data and trying to do imputation, I'm thinking like, oh, this is not missing at random. This is like, because like, when do I forget to put my Apple Watch on? I forget when I have too much going on. I forgot to charge it that night.
Yep. No, yes. So that's why, this is why I felt comfortable making that assumption in my setting, which was the hospitalized setting where nurses are checking on the person, I think every 30 minutes to make sure they're wearing the device and things like that. In the wild, okay. So the missing at random assumption is saying that conditional on what I've observed, the missing data is independent of the unobserved variables. So if you're worried that level of stress is what's really driving, or anxiety is what's driving the missing data, then if you collect anxiety over time, you might be able to say, well, conditional on the observed anxiety, it's missing at random conditional and maybe longitudinal trajectories that I observe. But I agree with you. What I would normally do in that setting is do a bunch of sensitivity analysis around that assumption, because I agree, I don't often feel comfortable with making that assumption. The other point that I would make is twofold. One is a really simple one, which is just often people pretend that when you design a study, you forget certain obvious things, like people will forget to wear the device no matter what, especially when they're stressed because of work or they have to give a presentation like today. And maybe, let's just pretend it's correlated. I didn't wear it because I had to give a talk today. That's why it's correlated, right? Reminders to wear sensors in the morning can be quite effective. So what I've seen is people just will always send a reminder in the morning to wear the wearable device. Like, we see that you're not wearing the wearable device, reminders. And you can sometimes use those to your advantage to get higher quality data, but it's still not going to be perfect. So the other point to note is that, Caroline, your question, yes, you'll have access to all my slides. I can send them to whoever I need to send them to, I'll send them to, so you can have access. The other point is just, what I often see is people aren't collecting enough information to know the reasons why and be able to disentangle things like the device is dead, meaning you have no battery life, compared to the person is not wearing the device currently. So in the example of sleep, often so this is the study I'm showing here, the Intern health study. What you're trying to measure is sleep over time. So just as an example, but often you have missingness in sleep. Why did we see missingness in sleep? Because the Apple Watch only has a battery that's about like 12 hours. So if you wear it during the day, you have to charge it at night. Like, unless you charge it when you're sort of eating or something, you're often going to have people who just don't have sleep data because of that. And so there, we just felt like we couldn't really get around it. And usually we just say, okay, that's more of a battery life issue than it is really an issue around sleep measurements being correlated with other outcomes. But we can't test it. So I'm with you, Jesse. It's like I make the assumption and then I'm like, I'm just explicit, at least. That's my goal.
We've collected this qualitative data when everybody's missing anything for more than 3 days. We call them, we get data, but then we'll have examples like somebody's not wearing their watch because they've been hospitalized. They're in the psychiatric hospital. So they can't wear their watch. But then do we call that missing at random? Because sort of that's like really not missing at random, but sort of it is, because they aren't even allowed to. So it's like the data is missing probably, so it's like,
yeah,
I don't know.
So
but
yeah, and I had a similar example.
Sensitivity analyses, basically.
Yeah, and so the question would be like, conditional on, I'll give an example that I'm more familiar with that's really similar, which is I was working on a study that has to do with substance use. And so individuals would end up in jail, and that's why they didn't respond to the surveys. So the question would be like, they'd actually drop out completely because the study was short and they would be in jail, so they couldn't get to their phone. So the point is, if you thought that dropout was correlated with, so if they were reporting their substance use over time, and you said, oh, it's I'm going to account for that in the missing data part, right? So it's missing at random because they had higher relative use. That might be an assumption you feel comfortable with. What I often do with these studies, because I don't feel comfortable with making strong assumptions, is first sensitivity analysis as much as you can. And then the second point is being explicit. As often people report missingness, but they don't report the reasons why things are missing. And so I think being more explicit as you can about why the data is missing and the reasons that you're seeing missing data. So from my perspective, knowing it's 30% missing, but breaking that out into it's missing because they weren't wearing the device, it's missing because our system broke, it's missing, like what were the reasons why I was seeing the missingness? It'll help people feel out whether the conclusions are generalizable or not. I have 3 minutes left, so I'm going to say one last thing and then I'll answer. I believe there's one more question in the chat. So what I will say is just so the Intern Health study turned out to be an MRT, and I just wanted to mention that means I have time varying treatments. So in this case, every single week individuals were being sent either mood, activity, or sleep notifications. And the analysis, for those of you who have seen MRT analyses, which I assume you'll probably either see before or we'll see at some point during the institute, those analyses look a lot like GEE analyses. So you might say, hey, I want to do imputation, and maybe I could use the mice package. And my only point I wanted to make before letting you go is that when you have time varying treatments, you have to be really careful when you impute. Why? Because if you're familiar with causal inference, one of the things you're concerned with is using post-treatment data to impute a current value. And so there's literature on sequential randomized trials and imputation, and what they recommend, and the recommendation I'll give to you today, is just carefully use the historical data, not future data, to do the imputation. So in the context of the Intern Health study, I want to analyze it like an MRT. So what we ended up doing, what the team ended up doing, and I have the data now, but I didn't do the imputation, was imputing current mood on the week given past moods and past data, but not using future data. And again, this is an issue around causal inference and worrying about what are you using to impute the missing data. And so in the context of causal inference, you're really concerned with this. And so I wanted to raise this point before you all head out, and at least give you the paper. So here, the key point is, if you're going to do anything with time varying interventions, you have to be I already said it's really complicated, it's really hard. Now if you're doing time varying interventions, it's even harder, and you have to be even more careful about how you do that imputation. All right, I'm going to end here with a few thoughts and just answer Carrie's question, which is my point here is just record everything you can, be explicit about the reasons for missingness, and always there's going to be a lot of missing data and messiness with your problem. Try and to make your life simpler, I always try and ask, what is your actual scientific question you're asking, and what scales do you have to worry about things? So if your questions are at the daily scale, then maybe try and avoid trying to impute minute-to-minute level activity and focus more on imputation of the daily step counts. So there's a lot going on, and sort of focusing your efforts is usually what I would recommend. I will, with my negative 30 seconds remaining, I just want to answer Carrie's question so I can finish here. So Carrie asked, do you think using a logistic regression with predictive variables predict whether an individual drops out is helpful? So in that case, if you have dropout and you're worried about dropout, one of the ways you can do it is you can actually model the dropout. And so one of the things you can do is actually, so typically you'll model dropout as a time to event outcome. And there are ways to handle time to event dropout and accounting for that in a joint model with the regression that you care about estimating. So there's a whole literature on joint modeling, where joint modeling is an idea of, I want to model, say, the relationship between positive and negative affect, but people are dropping out from my study, and dropout might be correlated with positive and negative affect. And so the joint model will account for those things. And so I would point you, Carrie, to that literature, which allows you to avoid bias in your estimates. But I think we're over on time, so I'm going to end here, and Pedro will let me know if I have time for questions or not.
All right, thanks so much, Walter. How about we do one more question if there is anything pressing, and then we'll transition to Eric, because I think we still have some people in Europe and it's getting later. so that we can end this on time.
Walter, very nice talk. I've worked a little bit with the Fitbit data, and a lot of the issues that you brought up, really resonated. And I guess one question I have is, you mentioned trying to understand missingness. How do you set your study up, especially when you're dealing with large data sets and data sets that are 6 months long of step data? How do you set your study up so you can evaluate missingness in a way that's meaningful?
That's a great question. So I think the thing that I normally do, and I'm coming from the world in which we're dealing with interventions too. So a lot of my concern is on the missingness due to intervention side. But let's just say you had Fitbit data for 6 months and you had missing. See, my dogs could only be trained until 4:02, and now they're going to lose their minds. So I think the best way to set it up would be so if you really wanted to model, like, let's say there was a primary aim of your study, right? And your primary aim was to look at longitudinal trajectories of step count over time and understand how they correlate with some baseline variables. I'm making it up, but that's this. Then what I would do is I would make sure that you really think about it, and it's at the daily level. I would think carefully about how are you going to, if you have missing data, decide why it's missing and therefore how you might impute it. So you'll always have a complete case analysis in mind, but you always want to think about what are you going to do with the missingness? How are you going to identify the types of missingness? And then how are you going to handle each of them separately? So in the case of daily level step count, how are you going to handle things like having half a day of step count? Are you going to impute the second half? Are you going to check the battery life and say, okay, we know it was missing because the battery died, and so we'll impute this way? I think just having a careful plan on your primary aims is usually the best you're gonna hope for, because you're gonna have other missingness problems. But I always sort of say your primary aim is the thing you want to sort of think most about, and so there it would sort of guide all of those decisions.
Okay, great. Thank you.
Yeah.
Wonderful. Thanks so much, Walter. This was great.